VFX, Shaders and SFX in XR Applications Development course, Chapter 2, Part 2. At the successful completion of this day's training, learners will be able to identify and differentiate between various types of shaders, distinguish when shaders are applied or not applied in an XR application or game, create and apply graph to materials and objects, use shader graph nodes and procedural textures to create advanced shader effects. In Unity, a shader is a small program that runs on the graphics processing unit, GPU, and determines how a surface is rendered. Essentially, it dictates the visual appearance of objects in your game. Here's a breakdown of what shaders do and why they're important. What shaders do: surface appearance. Shaders control the color, texture, and lighting of a surface. They can create effects like reflections, refractions, shadows, and distortions. Vertex manipulation. Vertex shaders can modify the position of vertices in a mesh. This allows for effects like wave distortions, animations, and terrain deformation. Pixel Chosh fragment manipulation. Fragment shaders, also known as pixel shaders, determine the color of each pixel on a surface. This is where most of the visual effects are created. Types of shaders in Unity. Surface shaders. These are Unity's high-level shaders, simplifying the process of creating complex lighting effects. They handle much of the lighting calculations automatically, making them easier to use for beginners. Vertex and fragment shaders. These are low-level shaders that give you direct control over the vertex and pixel processing. They are more complex but offer greater flexibility for creating custom effects. Compute shaders. These shaders use the GPU for general-purpose computing, not just rendering. They can be used for things like physics simulations or image processing. Unlit shaders. These shaders do not use any lighting calculations and simply display the color or texture that is assigned to them. In Unity, you can create and use shaders in several ways. Shader graph. Unity's shader graph is a visual tool that allows you to create shaders without writing code. It's a great option for artists and designers who want to create custom shaders without deep programming knowledge. Writing shader code. You can write shaders directly using shader languages like HLSL, High-Level Shading Language, or GLSL, OpenGL Shading Language. This gives you the most control, but requires programming expertise. Let's watch a video discussing shaders in Unity.
You guys see this? I've actually gotten tan. I think I've been out in the sun for too long. Luckily, today we're talking about shade. Earth. So Shader Graph is Unity's new node-based shader editor. It allows you to create all kinds of cool effects and generally just alter the visual appearance of your game. Shader Graph is a huge tool and can be used to create anything from flowing lava to holograms to sprite animations and post-processing effects. So far, all this stuff has been done by writing custom shaders by hand, but with Shader Graph we can do everything visually and in a fraction of the time. For someone like me who's just terrible at writing shaders, Shader Graph is an amazing tool, and I don't think I've ever been this excited about a Unity feature. Alright, enough talking about it, let's start using it. But first, this video is sponsored by Bolt. Bolt is an awesome visual scripting tool that allows you to quickly and easily program from within the Unity editor without writing a single line of code. The cool thing is that Bolt works in much the same way as Shader Graph. It's a completely node-based visual tool. However, instead of just creating shaders, Bolt opens up the full power of C# scripting in Unity, along with the ability to live edit your graphs while in play mode. Personally, I'm extremely impressed with this tool, as I think it combines the best of what I've seen from other visual scripting solutions. To get started, simply click the link in the description and download Bolt from the Unity Asset Store. Alright, it's shader time. So the first thing that we want to do is make sure we're using Unity 2018.1 or later. I'm using Unity Hub, so for me that means going to installs. And as you can see, I'm currently using 2018.1.1. We'll then create a new project. And here under template, we need to change to the lightweight render pipeline. Shader Graph is currently only available using this template, but support for other templates is coming. Now I've gone ahead and created a quick example scene. The only things that I have is a camera, a couple of lights, a tiny bit of post-processing, and of course this monkey. And as with any object in our game, this monkey has a material. The material is currently just using the standard shader. So let's change this by creating our own custom shader. We're going to be creating a cool glowy shader that looks like this. But first, it's a good idea to make sure that we're using the newest version of Shader Graph. To do that, we'll go to Window and open up the new Package Manager. Here we can see all the different packages currently in our project. You'll notice that the Shader Graph package isn't actually in here, but that's because it's part of the render pipeline's lightweight. In my case, this also has an update available, so I'm just going to go ahead and update it. So now we're on the newest version of Shader Graph, and we're ready to go ahead and create our shader. Let's right click in our project, go create, under shader, and here we can see the normal shaders, as well as 3 new options ending with graph. Let's select the PBR graph. We'll give this shader a name. I'm going to call it monkey underscore shader. And now to open this up in Shader Graph, we simply double click it. And this entirely new window is going to pop up. As with any other window in Unity, we can dock this anywhere we want or maximize and minimize it. I normally have this in full screen on my secondary monitor, but for now I'm just going to make it into a window and maximize that window. And by default, when we open Shader Graph, we have only one node. This is our PBR master node. Master nodes in Shader Graph represent our final output. Right away you will notice that you know most of these settings from the normal standard shader. We can change the albedo. I'm going to go ahead and make it some kind of blue here. That's a slot for normal, emission, metallic, and all that good stuff. And the cool thing is that instead of just controlling these through textures, we can now control them using different nodes. So in order to try and make our object glow around the edges, we need to modify our emission. However, if we just go ahead and change our emission for the entire object, well, we can see that the result isn't particularly interesting. Instead, let's go ahead and create our own node. By the way, to move around, you can use Alt and click or just the middle mouse button, and you can scroll to zoom. So to create a new node, we can either right click, go create node, or simply use the keyboard shortcut, which is space. This brings up a tiny panel where we have different categories for different nodes, and you'll quickly see just how many different nodes are actually in here. And on top of that, new nodes are constantly being added. So it's safe to say that we won't be going over all the nodes in this tutorial. So the node that we want to create here is what we refer to as Fresnel. So I'm just going to go ahead and search for that. And you can see it pops up. Let's click it, and voila, we've created a Fresnel effect node. Now, understanding how the different nodes in Shader Graph work can be extremely math heavy. Luckily, we can always see a visual representation of what the node is doing. So in terms of the Fresnel effect, it's creating this circular ramp, and we can control the power of that ramp using this value here. For now, I'm just going to set it to something like 3. We can then take the output of this node and drag it right into the emission input of our master node. And right away we can see that we get this glowing effect. So next, let's add a way to control the color of our Fresnel. To do this, we need a color node. So let's hit space, let's search for color and hit enter. Now this is a really simple node. It doesn't take in any inputs. Instead, we can just select a color. I'm going to choose some kind of bright orange. And we want to combine this with our Fresnel effect. To do that, we create another node. So let's hit space. And this time we want to create a multiply node. This of course allows us to multiply together 2 different inputs and get a result. So let's remove the old connection here by selecting it and hitting delete. And let's instead connect our Fresnel out with the first multiply input and the output of our color with the second multiply input. And right away we can see the result. We can then take the output of this multiply node and put it into emission. And voila, we can now use the color field to control the color of our Fresnel. So this is a really cool example of how this node-based way of thinking works. You combine together different nodes in order to create interesting results. And pretty much all nodes work this way. There's some kind of input, in our case the Fresnel and color. The node does some magical processing behind the scenes and spits out a result. And if you ever wonder what a node does, you can always right-click on it and hit Open Documentation. And this will open up a documentation page for that particular node with a description of what it does, which kinds of input and output it has, as well as the function that it executes behind the scenes. So that's really cool. Now there's definitely some more we can do with this. I'm going to change the color mode from default to HDR because we are working with emission here. And so I'm going to go in and bump up the intensity to say 1, just to make the glow a bit stronger. And of course, if we save this asset now and go back into Unity, we can easily apply it to our monkey. All we need to do is select our monkey material, and under the shader, we'll go under graphs. Currently, all shaders created with shader graphs go under here, but I hear the team is currently working to fix that. And we can then select our monkey shader, and we can see just how cool that looks in the editor. However, something that would be really neat is the ability to change the color of our Fresnel from inside the material. Because currently we have to double click on our shader, open it up in shader graph, find the correct node and make the change in here. And that's not very intuitive. And also it means that the color will be the same for all of our materials. Instead, we can right click on this color and we can convert it to a property. This makes it so that we can no longer edit the node in here, but instead it shows up in the top left corner. This is what we refer to as the blackboard, and here we can see all the properties that our shader has. In our case, we just created a color, and if we expand this, we can now see that we can change both the color and mode up here instead. We can also right click on it to rename it, and I'm going to rename it to Fresnel color. As a result of this, if we save this asset and select the material, we now change the Fresnel color in here. Awesome! Let's see what else we could do to make this more interesting. First of all, we can change the preview down here so that we can see it on our monkey head. To do that, let's right click and choose custom mesh, and we can then select the monkey head. That makes everything a bit clearer to see. We could then try animating our Fresnel effect over time. To do this, let's select all of our nodes and move them up a bit. Let's then create a new node. This time I'm going to search for time. Let's hit enter. And here we have all kinds of different outputs for time. Let's then create a multiply node. So space, multiply. I'm going to delete the old connection here and go from our old multiply node to our new one. And from our time node, I'm going to take the sign of time and drag that into the second multiply input. And we can see now this cool animation that occurs. Of course, this sign of time goes between -1 and 1, and we really only want it to go between 0 and 1. So we can actually remove this here and instead put a node in between. So we'll go from sign of time into, and we'll then create a remap node, and we want it to go to the input. So it's going from the sign of time to the input of our remap node. Our input goes between -1 and 1, and our output goes between 0 and 1. So now you can see that the animation looks much nicer. Let's then take the output of our remap node and drag it into the second input of our multiply. And finally, let's take the output of our multiply node and drag it back into emission. And there we go, we've now created an animated material. I don't want this effect to completely disappear at any point, so I'm going to make it go between 0.2 and 1 instead of 0 and 1. I think that looks a bit better. So we've now created a pulsating highlight. Let's just clean up our nodes here by moving them up a bit. Let's save the asset, close down shader graph, and hit play. We can see that our monkey is indeed animating. Woohoo! Now the final thing that I think is good to know when getting started with shader graph is how we can work with textures. To do this, let's start by creating a property in our blackboard. Here we have some different ones to choose from. We're going to select texture, and let's just create an occlusion texture for our model. So let's call this occlusion. And as the default input here, I'm going to select a monkey occlusion texture that I have prepared. We then take our property and drag it in here. And at this point, it would be pretty intuitive to simply go from the occlusion property into the occlusion input on our PBR master. But as you can see, it really doesn't accept this. The reason why is that there are currently two different types. As you can see on our PBR master, after occlusion, there's a 1 in parentheses. That's because the occlusion is a single channel value, whereas our property is parentheses t. That's because the type of our property is a texture. So to convert between these, we take the output of our property, we input it into a sample texture node, and we then go from this sample texture node into the occlusion input. And now it should work just fine. If we save this asset and select our monkey material, we now have an empty texture slot. Here we can then input our monkey occlusion. And as you can see, if we toggle between the two, it clearly adds some nice ambient occlusion to our model. So that's how you can apply texture nodes in shader graph. And that should be enough to get you started. From here on, it's just about playing around with it, trying to recreate different effects and figuring out what the different nodes do.
Shaders play a pivotal role in defining the look and aesthetic of a video game. They're not just about making things prettier, they're about crafting a specific visual style. Here's how. 1. Lighting and shadows. Realism versus stylization. Shaders control how light interacts with surfaces. Realistic shaders can simulate global illumination, ray tracing, and physically based rendering, PBR, creating lifelike lighting and shadows. Conversely, Stylized shaders can create exaggerated or cartoonish lighting, like cell shading, which gives a hand-drawn look. Atmosphere. Shaders can manipulate ambient lighting, shadows, and light scattering to create specific atmospheres, such as eerie darkness, warm sunlight, or foggy environments. 2. Texturing and surface properties. Material. Definition: shaders determine how textures are displayed on surfaces, including their roughness, reflectivity, and metallic properties. This allows for realistic materials like metal, wood, and skin. They can also create stylized textures, like pixel art or watercolor effects. Special effects. Shaders can create dynamic textures and effects, such as flowing water, fire, and explosions. 3. Post-processing effects. Color grading. Shaders can adjust the overall color palette of the game, creating different moods and styles. This is similar to color correction in photography or film. Visual filters. Shaders can apply various visual filters, such as blur, distortion, and chromatic aberration, to create unique visual effects. Artistic styles. Shaders can simulate artistic styles, such as oil painting, impressionism, or retro pixel art. Let's watch a video demonstrating how the use of shaders can transform the virtual world completely.
What's going on, guys? Freddy here, and today I just wanted to bring you guys a video kind of showing off Minecraft shaders and texture packs, because some of you may not know it, but this game can look 10 times better with just by installing some shaders and texture packs. So if you don't know, you can only get shaders on the PC version of Minecraft, but you can get texture packs on Xbox One and PS4, I know, but I'm not sure about mobile. But yeah, shaders are only on PC, so that's the only place you can get those. But they make it so much better, and texture packs do as well, but not as much as shaders. So here I built a house. As you can see in the default texture pack with no shaders, it doesn't look very good. The blocks aren't really mixed with each other very well. Like the sandstone doesn't look very good, and the cracked stone brick or chiseled stone brick or something like that doesn't look very good either. Like nothing really looks good, honestly. Glass looks horrible in the texture pack, and nether brick, like who would use that, right? But I'm gonna just flip on a couple of settings really fast, and you will see a drastic change. There's the shaders mod right there, and then we gotta get the different texture pack. Where's the resource packs? There we go. The modern HD one. That's what I use. Done. Oh, I quit. Oh, well, okay. Just load right back in. Okay, now look at the difference that made. Not only to the house, but look at the surroundings. Isn't it just so much crazier? I know some of you, a lot of you probably already know how much shaders and texture packs make a difference, but to those of you who don't, that's who this video is for, honestly. So yeah, I built this house, and in the other texture pack you could tell how it just didn't look good at all with the blocks that I chose, because that's because I built it in this texture pack with the shaders mod on. And oh, of course it starts to rain. How do I fix that? Oh dude, I'm great. I didn't even know that was a command. Squid, what are you doing? So yeah, I built this house in this texture pack, and I flipped it to the normal one just to see what it would look like, and it is such a drastic change. Like as you can see, these nether bricks don't even look like nether bricks anymore, and as we walk in, you can see this is so much more detail in the paintings, especially. Like look at this painting. It looks like an actual picture if you go a little ways away. You can't even tell that it's like a Minecraft painting. And this was like the Bean in Chicago, if you know what that is. It's like a huge art like piece of art. It's like a sculpture, and that's in this texture pack for one of the paintings, which is pretty cool. And just look at this view you can get from your house with a shaders mod. It makes the water look so much more realistic. It's so beautiful. I guess I'll just finish the tour of this house, because why not, right? The master bedroom and a balcony. You can look at all your cows in peace up here. And down below we have the bathroom. Because everybody needs a bathroom, right? Toilet, sink, shower. 2 shower heads because we're freaking rich, okay? Get off me. But yeah, as you can see, like the wood, it all looks so much better. This might not be very good for a survival world, this texture pack in particular, because it's like a modern-esque version of Minecraft. So that's why I use it to build modern houses, obviously. And I do really like building these, so if you guys want to see like a kind of like a let's play of me building it, leave that down in the comments below, and I could probably do that. This only took me about, I don't know, 2 hours, so I could chop that down and do like a 30-minute video probably. So yeah, I just wanted to show you guys the difference between this beautiful house and this not so beautiful house that you can get without shaders and without a texture pack. So without shaders, it still looks good, but not nearly as good as before, obviously. So many things just look so much more dull. And then we're back to the no texture pack, which just looks horrendous on the default texture pack. You can make stuff look good on default texture pack, but yeah. If you guys enjoyed this video, leave a like, comment, and subscribe for more. It's been Freddy. Thanks for watching. Peace out.
Geometry shaders in Unity and in graphics programming in general provide a powerful way to manipulate and generate geometry on the GPU. Here's a breakdown of what they are and how they're used. What geometry shaders do. Geometry manipulation. Geometry shaders operate on the output of the vertex shader. They receive primitives, points, lines, or triangles as input and can generate new primitives as output. This means they can add, remove, or modify geometry in real time. Dynamic geometry generation. They can be used to create effects like extruding geometry, generating particle trails, adding detail to low-poly models, creating grass or foliage, increased flexibility. Geometry shaders provide a level of flexibility beyond what vertex and fragment shaders can achieve alone. Let's watch a video demonstrating how geometry shaders are made in Unity URP.
Hi, I'm Ned, and I make games. Today I want to introduce you to geometry shaders in Unity's Universal Render Pipeline. With geometry shaders, you can create or destroy meshes and perform effects on triangles, all from the GPU. It might not seem like much, but you can do some truly magical effects with them. You cannot write geometry shaders in the shader graph, so if you've only made graphs before, this video will walk you through writing a shader in code. I made this project in Unity 2020.1.9F1 and Universal Render Pipeline 8.2.0. In this video, I'll make a shader that transforms each triangle of a mesh into a 3-dimensional pyramid. To get started, enable the Universal Render Pipeline by downloading the package, creating a settings asset, and enabling it in your project. Also set up a simple test scene and grab a texture. The main difference between a graph shader and a code shader is that in code, you have to separate your logic into a chain of several different functions, each running at different times, and then figure out how to pass data between them. For instance, all shaders have a vertex function, which runs once on each vertex of the mesh, and a fragment function, which runs once on each pixel displaying the mesh. Most of the logic you created in a graph would run in the fragment function. But if your lighting algorithm needs a world position and normal, you would first request this data in the vertex function. It would receive it in object space, transform it to world space, and then save it in a data structure for the fragment function to use later. Okay, so we'd have data for each vertex, but how does the renderer generate data for pixels between the vertices? If you think of each pixel as lying on a triangle, the value for any pixel can be generated by interpolating between the corner vertices. That's exactly what the renderer does for us automatically using a built-in system called the interpolator. Okay, so that's the theory. Let's get started by creating an unlit shader file called pyramidfaces.shader. This file will contain metadata, and another file called pyramidfaces.hlsl will contain the actual logic. You have to create that file in your operating system. While you're there, grab the nmg geometryhelpers.hlsl file from the video description. It contains some helper functions that I'll make use of. Open your .shader file. At the top, change the shader's name to custom/pyramidfaces. This is the folder and name which appears in the Materials Shader Picker dialog. Below that is a Properties block. This is where you put properties in a code shader. The main texture entry is already there, but add this float property called pyramid height. A subshader block can be used to generate several shaders for different hardware, but we'll ignore that for now. In the tags block, add this to tell Unity the shader is compatible with the URP. A pass block defines a render pass. Shaders usually have at least two passes, one for the forward lit phase, which renders lighting and color, and another for the shadow caster phase, which renders shadow maps. For this lit pass, delete the boilerplate code inside, and then tag it as a lit pass. These hash pragma lines define a bunch of metadata. First, we need to tell Unity which dependencies this shader requires, and register some shadow and lighting keywords. Next is where we register our shader functions. Unity will look for matching functions in the .hlsl file, which we tell it to include here. Alright, so open the HLSL file. This line makes sure the file is not accidentally compiled twice, and this line includes our helper functions. Next come the data structures. This attribute struct is the input to the vertex function, so request data that you need here. We need the position, normal, tangent, and UV. To request a value, you have to tag variables with these words called semantics. Unity will fill in the appropriate data automatically when it passes the structure to the vertex function. The vertex output struct is what the renderer interpolates and gives to the fragment function. Even here, where all values are set by the vertex function, we have to tag each field with a semantic so the renderer knows how to store them. You can stuff them all into these UV registers called textchord 0, 1, 2. Note the SV_position semantic must tag a vertex's position in clip space. Below that, we define variables corresponding to properties. This is mostly busy work, but it's required so code can access these properties. Make sure the names match the properties in the .shader file. Textures are special, and properties actually generate 3 different variables for them. One for the texture, the sampler, and the scale and offset data. Note the naming pattern. Finally, here is our vertex function. It takes in an attribute struct and outputs a vertex output struct. Use these URP functions to convert from object space to world and clip space. This transform text macro applies a texture scale and offset to the UV. Here is our fragment function. It takes in a vertex output struct and outputs a color. The svTarget semantic tells the renderer to store the returned value as the pixel's color. I need to initialize this lighting input struct and sample the main texture. Then I send all that data to the URP simple lit lighting function, which deals with lights, shadows, attenuation, etc. Back in Unity, create a material to use your new shader. This part should feel familiar. The mesh won't look too exciting yet, but we're just laying the groundwork. Okay, so I told you I'd teach you about geometry shaders. A geometry shader is just a shader with an optional third type of function that runs in between the vertex and fragment functions. The geometry function executes once per triangle in the mesh. It receives the vertex function's output for each triangle corner. Crucially, geometry functions can output a variable number of vertices arranged into triangles, allowing them to create, change, or remove triangles from the mesh. In the .shader file, add another pragma line to register a geometry function. In the HLSL file, we need to rearrange some data in our structs. Create a new geometry output struct, and give it the old vertex output fields. Now, the attributes and vertex output structs only need to contain position and UV. Simplify the vertex function to reflect this. The geometry function's signature looks a little intimidating, but really it just takes in 3 vertex output structs corresponding to a triangle on the mesh. It also receives an output stream, which we'll fill with the vertex and triangle data to create. Note that by default, if you add nothing to this stream, The renderer will render nothing. It will treat it as if the geometry function had destroyed all triangles. Finally, this max vertex count attribute tells the renderer the maximum number of vertices we will ever output. It's okay to output fewer, just not more. We'll create 3 triangles here, so 9 is perfect. I want to find the center position of the output triangle, as well as the triangle's normal. With that data, I can create a new center vertex and extrude it along the normal vector, constructing a pyramid. While I'm at it, I'll also find the UV for the new center point. This helper function will output one triangle containing the past 3 points. Let's look at it up here. This restart strip function tells the renderer that the next 3 vertices I output should make up a new triangle. Otherwise, vertices might connect in ways I don't want here. Each vertex in the new triangle should share a normal, so calculate that. This append function adds a vertex to the output stream, but not before setup vertex creates an output struct for it. Don't forget to change the fragment function to receive a geometry output struct. This will cause the geometry output struct to be interpolated and then sent to the fragment function. Now, back in Unity, we have the pyramids. That's the power of geometry shaders. You could even animate this, setting up very efficient mesh deformation effects. Before I go, I want to add a shadow caster pass, so this mesh will cast shadows. In the .shader file, duplicate the lit pass and change the tag to shadow caster. Remove the keyword pragmas and replace them with this one. Finally, define a shadow caster pass keyword, allowing our logic to slightly adjust when rendering a shadow map. Most of the Shadowcaster's logic is contained in the NMG geometry helpers file. We just need to change this one line. It calculates a vertex's clip space position, which is a little different when casting shadows, since Unity does some magic to try to avoid artifacts. In the fragment function, use a hash if block to immediately return 0 if we're in the Shadowcaster pass. There's no reason to calculate color here. And there you have it, a functional geometry shader written in code. The shader graph is very powerful, but there are still some things you can't create in it, and I hope this video will help you to not shy away from them. In the coming weeks, I'll show you some practical uses of geometry shaders, specifically in creating grass. Please subscribe and accept notifications so you don't miss the videos. Thank you so much. I'd also really appreciate it if you could leave a like. It lets YouTube know to recommend this video to others, and it really helps the channel. And of course, don't hesitate to comment if you have any questions. Do you have any ideas to use geometry shaders? Would you like to see me cover a certain topic in another video? Thanks so much for watching, and make games.
Let's reflect on what we have learned so far. In Unity, shaders are programs that run on the GPU, graphics processing unit, and tell it how to render each pixel on the screen. Think of them as instructions that define the visual appearance of your game objects. They determine things like color, what color a surface should be, brightness, how light or dark a surface should appear, texture, how textures are applied and sampled on a surface, reflections and specular highlights, how light reflects off a surface, transparency, whether and how a surface is see-through. Surface details, simulating bumps, normals, and other surface imperfections. Visual effects, creating special effects like distortions, outlines, and more. Here's a breakdown of their role. Controlling the rendering pipeline. Shaders are a fundamental part of the rendering pipeline in Unity. They sit between the object data, like vertex positions, normals, and UV coordinates, and what you ultimately see on the screen. Pixel level control. Shaders operate at the level of individual vertices and fragments, which become pixels. This allows for very precise control over the visual output. GPU acceleration. Because shaders run on the GPU, they can perform complex calculations in parallel for thousands or even millions of pixels simultaneously, making them very efficient for graphics-intensive tasks. Think of it like this. Imagine you're painting a picture. The game object's mesh is like the canvas and the basic outline of your subject. The material is like the type of paint and brushes you're going to use. The shader is the specific set of instructions you give to your brush strokes. It dictates how the paint interacts with the canvas, how colors blend, how light and shadow are applied, and any special techniques you use to create the final image. Key types of shaders in Unity. Unity offers different types of shaders to cater to various needs. Surface shaders. These are high-level shaders that simplify the process of creating physically based rendering, PBR effects, with realistic lighting. Unity handles much of the complex lighting calculations for you. Standard shaders. This is a built-in surface shader in Unity that provides a physically based rendering model and is highly versatile for most common materials. Unlit shaders. These are the most basic type of shaders. They don't interact with lights in the scene and simply output a color or texture. They are useful for UI elements, special effects, or when you want complete control over the final color. Compute shaders. These are not directly involved in rendering, but allow you to perform general-purpose computations on the GPU. They can be used for tasks like physics simulations or data processing. Vertex and fragment shaders, programmed directly. These give you the most control over the rendering process. You write the code that directly manipulates the vertices and fragments. This is more advanced but allows for highly customized effects. In summary, shaders are essential components in Unity that determine the visual appearance of your game objects by instructing the GPU on how to render each pixel. They are powerful tools for creating a wide range of visual styles and effects. Let's watch a video demonstrating basic shaders in Unity.